Okay guys, so this is Mrs. Davies and we're doing forces on incline notes today. So when you tilt something on its axis on an incline, you are changing the angle that your horizontal is lying on. Okay, so you still have gravitational, it always goes straight down. Your FG goes straight down. And if you have a surface, obviously you have a normal force that's still going straight up. Okay? So if this was like just sitting stationary on a block, okay, what happens is my gravity divides into two places with respect to this angle. So it's going to go, and I'm going to use dotted lines to show my components. I think I said that in the last video, so I want you to start doing that. Don't use straight lines for components, use dotted ones. And then your FG and the Y goes that way. So this angle theta is this angle theta. They are the same, okay? So you're splitting gravity and you're taking FGX and FGY with respect to a vertical axis, not a horizontal axis, okay? Okay. So, and if it's sitting stationary, then that means I have friction going this way. So I'm going to call it Fs for stationary friction. Okay? So your Fg is still mg, but your components are a little different now. So your Fgx, before, when you would take a component of something, it would be that component times cosine theta if it's on the x. But because this angle is taken with respect to the vertical, we're not going to do that. It'll be Fg sine theta will be on the x, and so then your vertical component of gravity, Fgy, will be Fg cosine theta. Okay, so if you flip your axes, then you have to flip where you get your sine and cosine from. Okay, your friction, any kind of friction, is still mu times normal, so that's not going to change. Okay, so that means when you do your summation equations, in this case, our static friction is equal and opposite to our Fgx. If it's sitting still, it's equal to 0. Okay, or if it's moving at a constant velocity, it's also equal to 0. But this will be equal to ma if it's accelerating. Okay. Your F net in the Y is just normal plus FGY, and that's going to be 0 pretty much all the time because it's not hopping up and down off the incline. It's not going up and down. It's just going side to side. It's just doing things horizontally. Okay, that's all. Okay, so knowing all of that, let's jump in and do a little math. Okay, so here's a situation. I've got a mass of 25 kilograms, and it's stationary. I want to know the magnitude of the frictional force and normal forces. Okay, so I know that gravity is going to go straight down. I know I will have components of gravity. I'll have one going to the side. That'll be my Fgx, and I'll have one going down into the surface, and that would be my Fgy. I have a surface, so therefore I have a normal, and if it's stationary, then I have some friction out the back. Okay, so first I'm going to start with my Fg. So my Fg is mg, so that's 25 times gravity, which I'm just going to use 10. So then that's 250 newtons. Okay. Then I want my Fgx. So my Fgx is Fg sine theta. So it's going to be 250 sine and my theta is 30, so this is 30 degrees. Okay, so that equals 125 newtons. And then I want to do my FGY, which is going to be FG, which is 250 cosine theta. So you plug that in your calculator and you get 216.5 newtons. Okay, so now I have most of my components. So now I need to solve for my friction, my Fs, and my normal. Okay, so look at my summations. So my summation in the X says that my friction, my friction plus my FGX equals 0 if it's stationary, which means my static friction equals FGX, which equals 125 newtons. So there's my static friction. Okay, so then I look at my Y, so my F net in the Y, my normal, plus my FGY equals 0, because it's not jumping up and down, which means my normal equals my FGY, which equals 216.5 newtons. So those are my two that it asked me to find. Just for grins, we could find mu s. Okay, so if I wanted that, I know that my Fs for static friction is equal to mu s times normal. So if I wanted my mu s, I would just divide both sides by mu normal. My F normal. So now that I know both of those, it's just 125 over 216.5, which gives me, so my mu s is 0.58, which makes sense. It should always be a number less than 1, because if it were 1, that would mean that there's no friction. If it were 1, that would mean that there's so much friction that the thing won't move ever, ever, ever. So that's not going to happen. And it's never going to be greater. You can't have more friction than normal force. That's impossible. Okay, so it's always going to be a number less than 1. The greater the number is, though, the rougher the surface. Okay, that's pretty much it for that. All right, moving on. Got a few fun multiple choices. Okay, so the first one. So a crate is sliding down an incline ramp at a constant speed. The vector sum of all forces acting on this crate must point, well, if it's moving at a constant speed, then all forces are balanced. So the vector sum of all forces is 0. So it has to be E. Okay? Because they're all balanced. They're not going to go one way or the other because they're balanced. It doesn't matter that it's sliding. It's sliding at a constant speed, which means the friction is equal and opposite to FGY. Okay? It's asking for the vector sum of all forces, not the acceleration. Acceleration is always downwards, but anyway. Okay. So number 3. So we have a block of mass M sits on a rough inclined ramp that makes an angle theta with the horizontal. What must be true about the normal force of the block keeping it on the ramp? Okay, so if I'm looking at my object, right, I've got my FG, I've got my F normal, I've got my FGX, and I've got my FGY. So I must have my static friction there because it's at rest on the ramp. Okay, so see how my Fn is equally done but opposite my FGY? which means my Fn must be equal to my Fgy. My Fgy is Fg cosine theta. Fg is mg, so that means my Fn equals mg cosine theta. So that's my answer. Okay. Number 4. All right, so number 4, I've got 150 Newton crate being pulled up a perfectly smooth ramp. If it's perfectly smooth, probably ain't no friction. So let's keep reading, see if they talk about friction, okay? So it's pulled up a perfectly smooth ramp that slopes upward at 15 degrees by a pull that is directed 30 degrees above the surface of the ramp. What is the magnitude of the pull required to make? Okay, so we have a ramp that's at some degree, right? The degree is 15. And off of that ramp, you have a tension force that is 30 degrees above the surface of the ramp. So here's my ramp. Here's my thing that's on it. So I'm saying I've got some Fg. I've got some F normal. That's ugly, sorry. It's a perfectly smooth surface, so there's no friction. So I'm going to break up my Fg into components. Okay, so I've got Fgy, and I've got Fgx, and it's being pulled up the ramp. But here's the thing, it's being pulled up the ramp at an angle to the ramp. So my tension is actually being pulled up like this at an angle of 30 degrees. So this angle is 15 degrees and this angle is 30 degrees. Which means I have a tension force in the X and a tension force in the Y. Yay, more things. Okay, so I'm going to start with my Fg. So it's a 150 Newton crate. So that's telling me my Fg is 150 newtons. You don't have to do math for that. It's just that, okay? Okay, so then I can find my Fgx and my Fgy. So my Fgx is 150 sine 15. So that's 38.8 newtons. And my Fgy is 150 cosine 15. And that gives me 144.9 newtons. All right, now my F in the X direction, I have my tension component in the X, plus my Fgx, and it's being pulled up a perfectly smooth ramp at a constant velocity. If it's a constant velocity, then that means the net forces in the X are going to be 0, which means my tension in the X equals my Fgx. Okay. So my T in the X direction, because it is taken with respect to the horizontal, not the vertical. So my Tx is T cosine theta equals my Fgx. So I don't know my T. I'm looking for my T. So I'm just going to divide both sides by cosine theta. And that should get me my T. So my Fgx is 38.8 divided by cosine of 30. And you get 44.8 newtons. Okay, and I believe we are done with the notes packet at this point. So that's kind of nice, and I will see you in class. Goodbye.